Recently, very important news has emerged about dark matter and JUICE mission. The first news with us says, tiny black holes left over from the Big Bang may be prime dark matter suspects. When it comes to primordial black holes being dark matter suspects, their alibi may be falling apart. Tiny black holes, created seconds after the birth of the universe, may survive longer than expected, reigniting a suspicion that primordial black holes could account for dark matter, the universe's most mysterious stuff. Dark matter currently represents one of the most pressing problems in physics. That is because, despite making up an estimated 85% of the matter in the cosmos, dark matter remains effectively invisible to our eyes because it doesn't interact with light. Because the particles that comprise atoms that compose everyday stuff we can see, like stars, planets, and our own bodies, clearly do interact with light, this has prompted the search for dark matter particles outside the standard model of particle physics. Many scientists believe the answer could still lie within the standard model. However, if we consider a diminutive cousin of cosmic objects we usually view as tremendously massive, and even monstrous black holes. Max Planck Institute scientists from the University of Lisbon are two researchers who have recently been involved in such studies. They posit tiny black holes born over 13.8 billion years ago, just after the Big Bang, that are no larger than a proton, could cluster to become suspects for dark matter without the need for new physics. Not only has a recent change in thinking regarding how black holes evaporate prompted a reassessment of primordial black holes' viability as dark matter suspects, but as the search for a dark matter particle continues to mostly draw a blank, more researchers could begin to look at the primordial black hole dark matter theory more seriously. What are primordial black holes? As the name suggests, primordial black holes are a type of black hole that is formed at the beginning of the universe. Within the first fraction of a second of the universe, in fact. He explained that all the structures we observe in the universe, from superclusters of galaxies to the galaxies within themselves, are formed from slight overdensities in space present during the early universe. If the early universe experienced much stronger density fluctuations than those which created these features, and these fluctuations collapsed at an earlier time than galaxies indeed formed, then those overly dense patches could have spurred primordial black holes. Depending on the time at which this collapse may have happened as well as the scale of the collapse, these primordial black holes would have very different masses. The primordial black holes considered possible dark matter candidates would have masses ranging between a few tons and 1,000 tons, to be specific, which is less than the mass of a planet and more in the category of a small asteroid. Considering how the smallest black hole scientists have discovered to date, known as stellar mass black holes, have masses equivalent to between 3 and 50 times that of the Sun, which itself is 22 followed by 26 zeros tons. These primordial black holes are incredibly tiny. Still, primordial black holes are going to be incredibly difficult to confirm as dark matter, if they really do explain the phenomenon. Again, their light-trapping nature means they are effectively invisible. Plus, at such diminutive sizes, they don't have the same immense gravitational effects as their stellar and supermassive brethren. Even then, should a cluster of primordial black holes be detected, there is no real way to tell the difference between lots of little black holes and one large black hole. The last news with us says. In a virtual reality universe, upcoming JUICE mission flies by Jupiter's moon Callisto. Though it's still 7 years from reaching Jupiter, the JUICE mission is proceeding apace, and a recent test run simulated the mission's spacecraft flying by the Jovian icy moon, Callisto. Having blasted off from Europe's spaceport in French Guiana a year ago, the Jupiter Icy Moons Explorer, known as JUICE for short, is still in the inner solar system, getting ready for a series of gravity assists that will throw it onto a trajectory allowing it to rendezvous with Jupiter in 2031. Its first port of call will be the giant planet's outermost Galilean moon, Callisto. This will mark the first of 35 planned flybys of the gas planet's moons Callisto, Ganymede, and Europa, before the spacecraft settles into orbit around Ganymede. At the European Space Operations Center in Germany, the mission team is already preparing for this first flyby, but while using the engineering model of the spacecraft. This is an exact replica of the flight model that's currently cruising through space, with the same hardware, software, and instruments. The only difference is that it is sat in a clean room in Darmstadt. The problem that JUICE, and indeed any mission to Jupiter, faces is a time delay. How long it takes radio signals to reach the spacecraft from Earth and vice versa. This relay can take 33 minutes when Jupiter is at its closest to Earth and 54 minutes when it is on the other side of the solar system. Thus, JUICE is programmed with software that can think and plan autonomously without waiting for commands. One example of where JUICE's autonomy will be vital is when observing surface features on Callisto during flybys. Because we can't know JUICE's exact position when it passes through Callisto's gravitational field, however, the onboard computer must take over and fine-tune the spacecraft's orientation so it can target individual surface features with its instruments to an accuracy of a fraction of a degree. We need JUICE to be able to react with its own eyes and its own brain. When Callisto appears in the field of view of its navigation camera, it needs to be able to identify important features on the Moon's surface, rotate itself to point its instruments at them, and then continue rotating to keep them in view as it flies past. The team at ESOC had to make the engineering model believe it was really in space and flying past Callisto by projecting computer-generated images of Callisto into the model's navigation camera. The images mimic the orientation and phase that Callisto will have when JUICE does the flyby for real in 2031. The navigation software had to react to these images. If it noticed that it was approaching Callisto at the wrong angle or facing slightly the wrong direction, it had to attempt to correct these errors without our help. 3 days were set aside for testing at ESOC, and it was not expected to be plain sailing. The entire point of these practice runs is to smooth out the kinks. Because of the complexity of the task, it wasn't feasible to test on a software simulator first, where most of the gremlins could be ironed out. Instead, the JUICE team expected to have to endure a lot of trial and error, as well as rewriting of software, to get it to work. Yet, the engineering model succeeded on day 1, successfully targeting the images of Callisto and keeping locked onto locations on the Moon's icy surface as it performed a virtual flyby, rolling to keep the Moon in view. Thank you very much for watching. Goodbye.